Okay, finding first and second derivatives and evaluating those at given values. So we have kind of a complicated looking original function f of x here. It's a 7th degree polynomial. So let's jump right in. When we're taking the first derivative, all we have to do in this case is really use the power rule over and over and over. All right, so we'll be diligent one term at a time as we go through this. Just be careful. Like the 7 comes down, we reduce the exponent by 1. So 7 minus 1 makes 6. Minus, now power rule again, right? So the 5 comes down, you multiply it by the 3, you get 15 x to the 4th power as we reduce it by 1. Next up, plus 9x squared, same idea, right? Same power rule, minus this linear term is going to make just the coefficient out in front is going to be 3, and the derivative of the 1 at the end is going to be 0. So I'm going to leave that off. Next, we want to evaluate this at 2. So let's go ahead and replace each one of the x's with 2's. So we have 7 times 2 to the 6th power, minus 15 times 2 to the 4th power, plus 9 times 2 squared, minus 3. Now at this point, you may elect to get your calculator out. I completely understand. This works out to be pretty big numbers as we work through this. So 7 times 64 minus 15 times 16. Plus 9 times 4 minus 3. We could work it all out, but eventually we're going to get to 391. I don't think that's the insight I'm going to be able to provide in this class, in this video. All right. Next up, let's find f double prime. So to get the second derivative, what we want to do is we want to use the first derivative and take its derivative again. So again, it's going to be power rule, but we're focused on the first derivative. So 7x to the 6th, as we take its derivative, the 6 comes down, gets multiplied by the 7. We're going to get 42, and then we reduce the exponent by 1, so 6 minus 1 makes 5, minus, power rule again, 4 comes down, multiplied by 15 is going to give us 60. Reduce the exponent by 1, x cubed, plus 2 comes down, multiplied by the 9, 18. X to the 1st power as we reduce that by 1, and then the 3 is a constant. Its derivative is going to be 0. So I'm going to leave that 0 off. Evaluating this at 2, well, that means over on the right-hand side, we're going to replace each one of those x's in the second derivative with 2's. Do a little bit of simplifying down, showing my work here, but I get if you're like, calculator, here we come. 2 to the 5th is 32 minus 60 times 8 plus 36 here at the end. Works out to be 900. All right, so what information does this actually tell us at an x value of 2? All right, because the first derivative turned out being positive, because 391 is a positive number, the first derivative always tells us about a graph. This is the instantaneous rate of change, or on a graph, we can think of that as the slope of a tangent line. So because the slope of a tangent line is positive, that means the graph is increasing at an x value of 2. That's based on the first derivative. Now the second derivative, because this is positive, 900, when we evaluated it at 2, that tells us about concavity of the graph. So concave, because it's positive, we would say our graph is concave up and look like the bottom of a bowl, some portion of this either on the left-hand or right-hand side at that x value of 2. All right, so I hope this helps out as you are taking a look at this. In fact, as I think about it, it's going to have to be the right half here based on the information. Now, why it has to be the right half is, remember, our graph is increasing. So if I were to draw a tangent line to our graph in here, it's going to be some portion on the right-hand side where it's both increasing and concave up. Hope this helps out as you're working on finding first and second derivatives, evaluating them, and understanding what that tells you about the graph. Good luck.